Geotechnical Engineering, Part A, Soil Mechanics, Session 7, Shrinkage Limit in Atterberg. So we are going to talk about shrinkage limit, which is one of the Atterberg limits. So in shrinkage limit, fine grained soil when losing uh, its moisture content, it shrinks. So the moisture content in which the reduction in volume stops called shrinkage limit. In other words, soil shrinks as moisture is gradually lost from it. With continuing loss of moisture, a stage of equilibrium is reached at which more loss of moisture will result in no further volume change. So if we call this initial a volume like Wi, we start drawing the sample. So if this is W, this is W, this is V. As we start drawing the sample, losing moisture content, the volume is dropping, reducing, until we reach to a point that from that point there is no further change in the volume. So that point called shrinkage. So fine grained soil when losing their moisture content shrink. The moisture content in which the reduction in volume stops, like 0.3 here, it called shrinkage limit. Let's go a bit deeper to shrinkage limit formula to derive it mathematically. So SL, if we call this point shrinkage limit, because there is no, by drawing it up, losing the more moisture content, there is no further reduction in volume. So volume remains constant from point B forever. So that's a Wi initial moisture minus delta W. If we're traveling from point 1 to shrinkage limit, initial moisture is Wi plus this amount delta W, and we reach to shrinkage limit 0.3. So shrinkage limit is equal to Wi minus delta W. And delta Wi is just moisture content is mass of water over mass of solid soil grains, and that's equal to, when you draw a sample come truly, the leftover is just mass of final, and that's nothing but mass of soil, and mass of W is just initial mass, which is the wet mass, minus soil mass, which is a mass or weight of water, or for our case mass of water. And delta W is variation of mass of water over mass of soil. And because if we show the numerator mass of water like density of water times volume of, and the denominator mf, mass of final, is mass of soil. So we can take the final mass out of the delta. So that's 1 over mf times the variation of rho w vw. If you rewrite the equation, it just gives you delta w, change in water content, is 1 over final mass times rho w, because that's constant, times delta volume of total. And that's V initial minus V final. Amount of water we lose is delta volume total. That's initial minus final, and the only thing is removing is the water content. If we just write the delta W, that's 1 over mass of final times rho W times in parentheses Vi minus Vf initial minus final volume. And if we just replace these two equations back in shrinkage limit and add up them together, it just gives us the total complete SL formula. If you multiply it by 100, that's a shrinkage limit percentile. That's shrinkage limit percentile. So let's take a look to Atterberg limits once more. So if you dry the sample, you move this direction. If you wet the sample, you move this direction. That's volume. That's percent of moisture content. LL stands for liquid limit. When you locate at liquid part, then move to plastic limit. Then PL is the boundary of semi-solid and solid. And shrinkage limit is mass of solid and semi-solid. These are the Atterberg limits, which we focused on shrinkage limit session. Let's put it to an example. A saturated soil sample has initial volume of 55 centimeter cube and weight of 100 grams. If the sample is dried completely, if we entirely dry the sample, and then its volume and weights reduced to 85 gram and 50 centimeter cubes, respectively. Calculate shrinkage limit. We want to know what the shrinkage limit is. So that's simple enough. If we have initial volume and weight, and we have final volume and weight, by just applying formula which we just a moment ago derivated, that's shrinkage limit, and we just replace the initial mass minus final mass, which is 100 minus 85, 100 gram minus 85 gram, and minus Vi initial volume, which is 55 centimeter cube minus 50, and in terms of times rho W, which is 1 gram per centimeter cube. And then if you replace it in the formula over mass final, which is 85 grams, times 100, it just gives you shrinkage limit is equal to 11.76%.